Picture this. Fast-forwarding through a cosmic security tape spanning 10 million years, only to see every crossroads, every bend, every path you inspect dead-ending into emptiness. That's the bizarre reality astronomers encountered while probing the third confirmed interstellar intruder to grace our solar system. In July 2025, the object dubbed 3 Atlas hurtled into sight, prompting global teams to swivel the Hubble, James Webb, and various Earthbound scopes its way in mere weeks. Tracing its orbit backward ought to have been straightforward. Pinpoint the star that ejected it, chart the pull of gravity over time, and wrap things up. But instead, they hit a blank slate. No significant interactions turned up across a 10-million-year probe. Its composition defies norms. The surrounding dust acts unlike any recorded sample, and its path implies it's been wandering since long before our sun sparked to life. Stick around till the finish. We'll unpack why this enigma rattles experts on cosmic beginnings and what it signifies when such a wanderer dodges the ultimate query, its true birthplace. Part 1. 3 Atlas haunts like a specter. To kick things off properly, because the revelations ahead will stun you. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System outpost in Chile detected a flash slicing through the inner solar system. Hours later, skywatchers confirmed it as just the third verified interstellar visitor to our cosmic backyard. They named it 3 Atlas, though for the rest of our expedition tonight, we'll stick to calling it Atlas. Turning to those astronomers, they aimed the planet's top orbital and terrestrial instruments at it. Hubble, James Webb, observatories spanning the world. Next, they attempted the standard protocol for spotting a drifter, backtracking it to its source. And that's when the weirdness kicked in. A group under Perez Cotto's lead dropped a 2025 paper that promised to be unremarkable. Their goal? Essentially, to reverse the universe's surveillance footage. They plotted Atlas's route in reverse across space and epochs, aiming to identify the star that hurled it into the abyss. Drawing on Gaia Data Release 3, our finest ever star-by-star inventory, they mapped millions of celestial bodies in full 6-dimensional detail. Locations, velocities, the lot. Simulations rolled back 10 million years, pitting Atlas's course against every local star in the archive. The probe spanned a 500-parsec cone, equivalent to about 1,600 light-years, a vast swath of the cosmos. It highlighted 93 potential close calls, stars that could have tugged Atlas gravitationally toward its present route. Yet everyone flopped. 0 real influences. The nearest viable star, catalogued as GIADR 36863591389529611264, zipped by at roughly 0.30 parsecs, around 98,000 astronomical units, with a closing speed of 35 kilometers per second. The catch? Crunching the gravity jolt from that pass yields a speed shift for Atlas of about 5 times 10 carat minus 4 m/s. That's a mere 0.5 millimeters per second, way too puny to account for its actual path. It's not even in the ballpark. Let me boil down the riddle plainly. Atlas follows a hyperbolic trajectory, proving it originated beyond our solar system. No debate there. Such intruders don't pop out of thin air, they must hail from someplace. But scouring that someplace yields zilch. No gravity scars, no originating star, no stellar kin. Across all our records, it's an utter space waif. Unless you chalk this up to skimpy info, note that the researchers incorporated Monte Carlo runs on orbit variances, covariance ellipsoids, every bell and whistle. They factored in observational glitches, tested alternate frames, and synced with rival origin hunts. The verdict stayed firm: origin unknown. Yet, an intriguing twist prevents total bewilderment. Though Atlas boasts a hefty oddball speed against the local rest frame, its dynamics align with the Milky Way's thin disk. Chart its velocity in galaxy-based chords, plot Tumor diagrams, run probability checks. It fits the profile of the youthful stellar cluster dominating our locale. Not some relic from the galaxy's far-flung halo fringes. It travels as if native to these parts. So if it's local, how come its roots evade us? The find sparked an international frenzy right away. Chile's Atlas nabbed it first, then Hubble zeroed in. James Webb's infrared gaze followed suit. Telescopes from Hawaiian peaks to South African plains monitored it round the clock. Far from a dim blur in isolated logs, Atlas morphed into one of the sky's most scrutinized targets virtually overnight. Despite the barrage of scrutiny and data deluge, though, we can't tackle the simplest probe any finder would pose. What's your starting point? Grasp this. An untraceable interloper upends everything. What this really signifies is that experts have scoured for evidence of its origins, only to conclude there's no clear path. Not within the databases or techniques available to us today. Picture yourself reviewing footage from a dashboard camera. You're instructed to reverse it and spot the final bend the vehicle took. You go back 10 seconds, then a full minute, even an hour. But the farther you rewind, the highways begin to fade into obscurity. Crossings blend together indistinctly. Road lines fade into static. Once you've gone back 10 million years, the vehicle remains on the path. Yet every junction you inspect, every off-ramp you scrutinize, fails to match its starting point. The route just fades away into disorder. In the realm of interstellar object studies, this goes beyond a mere curiosity. If Atlas can't be connected to an originating stellar setup, the whole initiative to chart galactic chemical development via these nomadic boulders grinds to a halt. The concept was sophisticated. Intercept an interstellar comet. Examine its makeup. Follow its trajectory to a parent star. Leverage the star's age and metallicity to pinpoint when the comet formed. Repeat this with scores of such cosmic travelers, and you construct a chemical blueprint of planetary setups throughout the galaxy. However, if that initial phase, the backward trajectory, falters for causes we don't completely grasp, what's the fallback? A word of warning is in order. Being untraceable today doesn't guarantee it stays that way indefinitely. It simply means our current star lists and approaches fall short. Upcoming Gaia data updates could plug those holes. Sharper astrometry might narrow the orbital ambiguities. Fresh catalogs of motion for dimmer stars could uncover a progenitor we're overlooking now. The cosmos conceals its mysteries not out of spite, but because our observational tools aren't refined enough yet. Still, as of this moment, with our top-tier information, Atlas lacks any discernible lineage. And that's disturbing on a level deeper than simple uncertainty. So, if we can't follow its source through motion dynamics, might we deduce its origin from its composition? That's the following strategy. If trajectory calculations stay silent, perhaps its chemical profile will speak. After all, when the James Webb Space Telescope aimed its spectrometer at Atlas back in August 2025, the readings were utterly peculiar. The gases venting from it, the surrounding haze of vaporizing frost, none of it matches the typical comet profile. Not by a long shot. Part 2. The unsuccessful quest for its ancestral star. Allow me to guide you through the precise way the search for Atlas's home system unfolded. This wasn't some imprecise speculation. It was a detailed probe amid millions of possibilities, spanning timelines back to when early humans were mastering basic implements. The process unfolds like a detective thriller, except the evidence spans 10 million years, and the suspects are celestial bodies. First phase. Perez Cuto and their colleagues drew from the Gaia Data Release 3's premium 6-dimensional catalog of stars. This includes more than sky positions, its positions, motions across two axes, distance via parallax, and speeds approaching or receding via radial velocity. 6 metrics per star. They applied strict filters for reliability. Parallax exceeding 2 milliarcseconds to focus on closer systems. RU, the renormalized unit weight error, below 1. For to confirm solid astrometry. Minimum of 8 observation windows to sidestep anomalies. Following those selections, they ended up with 3.6 million stars boasting complete radial velocity info. 3.6 million possible progenitors. Second phase, starting positions. To reverse any path, you must first establish its current spot and speed precisely. They employed the pre-perihelion heliocentric vector computed by de la Fuente Marcos and team in 2025. Heliocentric indicates sun-centered measurements. But for galactic orbit simulations, they shifted to galactocentric frames, centered on the Milky Way's hub. That shift demands accurate knowledge of the sun's velocity against the local standard of rest, the typical drift of nearby stars. A misstep there skews the entire reversal. They avoided that error. Third phase, select the gravity model. The Milky Way isn't a single lump of mass. It's a rotating disk of stars, a central cluster of ancient ones, and a dark matter envelope encircling it all. For reliable orbit computations, a comprehensive model is essential. They opted for the MW Potential 2022, a cutting-edge representation of galactic gravity. They ran simulations via the Gala software package. Backward 10 million years, incrementally, factoring the galaxy's pull on Atlas and each potential star. Now, the challenging part, orbit imprecisions. Atlas's location and speed aren't known to perfect accuracy. Tiny discrepancies now amplify massively over 10 million years. Thus, they didn't perform a single run. They drew samples from the orbital covariance ellipsoids, executing Monte Carlo iterations. Hundreds of marginally varied various paths for Atlas's path emerged from the analysis, all aligning with the measurement errors. Should any path lead to a near pass by a star, that star gets marked as a potential origin. Yet, the real twist comes next. Despite broad Monte Carlo simulations and inflating errors to handle chaotic effects, zero-close approaches proved a viable source. Allow me to share the key stats. There were 93 standard passes inside 2 parsecs. Among them, 62 exceeded a 2 sigma confidence level. That seems hopeful, doesn't it? 93 opportunities to spot an origin. However, once you compute the energy transfer, the velocity shift from each pass, they all amount to zilch. The most powerful, that Gaia-identified star from before, delivers a speed adjustment of roughly 5 times 10m/s. Utterly insignificant. To put it in perspective, a person strolling displaces more push on nearby air particles. Gravitationally, this is a total dud. So why does a 0.30 parsec gap at 35 kilometers per second qualify as insignificant? Tidal effects drop off with greater separation and rise with closing speed. Fast-moving bodies experience only fleeting gravity pulls. No opportunity builds up significant push. Picture attempting to snatch a baseball while zooming by on a bike at freeway pace. Your grip hovers close for mere instants. Hardly any impact gets applied. That's the scenario unfolding. Except the bike's a star, the ball's Atlas, and the road's our galaxy. Fellow researchers conducted comparable investigations. Go's team in 2025 tweaked starting parameters, adjusted parallax error fixes differently, and arrived at varying pass counts. Their figures don't align precisely with Periscuto's. Crucially, though, the overall result holds. No clear-cut parent star, no encounter that could reasonably account for Atlas's path. Variations lie in the minutiae, not the outcome. After sorting through variances, like frame of reference picks and sampling methods, the narrative remains steady. Atlas stands alone, unlinked. Why cap the review at 10 million years? 2 factors. Chaos. For one, star paths and interstellar wanderer routes branch wildly over time from small nudges. Push further into the past, and backward calculations lose reliability. No longer charting true events, just random scatter. Next, data constraints. Gaia's speed toward us readings thin out past 500 parsecs. Vast swaths of galactic stars lack any such measures. Thus, even if Atlas hailed from a star at 2 kiloparsecs, we'd lack the info to verify. 10 million years marks the feasible limit where retracing holds scientific weight. Past that, it's mere speculation and shadows. What does it signify that Atlas's motion matches the galaxy's thin disk kinematically? Its travel through space, via U, V, W speed parts, slots into the norm for youngish disk dwellers. It doesn't behave like a halo wanderer, with wild loops, tilted paths, and swift drifts from the neighborhood rest frame. But note this, it doesn't reveal Atlas's precise age or metal content. Disk alignment is probabilistic, not a life story. It dismisses wild ideas, like an extragalactic visitor or ancient halo survivor, yet fails to nail down a birth setting. Dynamics have reached a dead end. Backward orbit mapping, the method to uncover Atlas's roots, yields no leads. We've probed as deep as possible with available observations. Scanned millions of stars. Factored in all ambiguities. The path runs dry. Still, perhaps the body itself reveals what its speed won't. Atlas isn't merely inert stone. It's venting. It's shedding gas. enveloped in a haze of vaporizing frost and grains. And when the James Webb Space Telescope examined that haze, it detected an anomaly defying known templates. The emissions from Atlas are downright bizarre. Part 3. The CO2 Haze Riddle. On August 6, 2025, James Webb aimed its near-infrared spectrometer at 3I/2025. The body sat roughly 3.32 Australian dollars from the Sun, tucked just shy of Jupiter's path. Webb snagged a full-field spectrum of the haze, the gas and grain envelope around the core. The discovery? A haze ruled by carbon dioxide. The 4.3-micron Nu-3 CO2 signal blazed bright, undeniable. Water appeared too, alongside carbon monoxide, hints of carbon sulfide, water ice dips, and particulate traces. CO2 stole the show, though. Abundant CO2 everywhere. Here's a figure underscoring the oddity. The blend fraction, CO2's share versus water, clocked in at 7.6 plus or minus 0.3. Among the topmost CO2 to water proportions recorded. No comet has ever shown CO2 levels like those detected in Atlas. To put it in perspective, the vast majority of long-period comets and those in the Jupiter family exhibit CO2 to water ratios far under 1. Water is the main player, with CO2 playing a minor role. Yet Atlas turns that dynamic upside down. Here, CO2 leads as the primary volatile substance, while water plays second fiddle. The sole comparable case is C/2016 R2 Pan-STARRS, which displayed exceptionally elevated CO2 levels. Even so, that was an anomaly amid hundreds of observations. Atlas is stepping into a rare, peculiar group. The structure of the coma brings in yet another intriguing aspect. Observations revealed boosted gas release on the sun-facing side, which aligns logically. Solar radiation warms the surface, causing ice to turn directly into vapor. Gases escape more readily in the direction of the sun. The puzzling element, though, even with this evident activity and the uneven distribution in the coma, Atlas's path shows no clear signs of non-gravitational push. I'll expand on that soon, but keep it in mind for now. We see a lively coma, yet no obvious thruster-like influence. That's noteworthy. What insights does a CO2-heavy coma offer about the origins of this object? The frost boundary for carbon dioxide ice lies farther out from the sun compared to water ice. Within a young star system's disk, the CO2 ice line usually extends past the water one. Since CO2 vaporizes at cooler temperatures due to its greater volatility, a high CO2 content in Atlas points to formation in a chillier zone of its home system, beyond the CO2 frost line, or perhaps some alteration that stripped away surface water but spared the CO2. Two main scenarios emerge, and they could overlap. Scenario 1. Atlas possesses a core that's inherently loaded with CO2. It might have originated in the distant fringes of a planetary setup where CO2 ice was plentiful. Alternatively, radiation over millions or billions of years could have altered its surface, transforming water ice into intricate organic compounds and isolating CO2. Or envision a crust of dust and tough materials acting as insulation, trapping water ice deep within while allowing more easily released CO2 to surface. Scenario 2. Limited heat reaching the interior. At distances of 3 to 4 astronomical units, the sun's warmth may not penetrate far enough to activate hidden water ice. With its reduced sublimation point, CO2 can release from nearer to the top, creating the illusion of a CO2-led coma despite water possibly being more abundant overall. As Atlas approaches perihelion at about 1.36 to 1 Australian dollar and 40 cents, water activity should ramp up. Should the ratio decrease, Scenario 2 gains ground. If it remains elevated, the first idea strengthens. Contrast this with the notable interstellar guest 2I/Borisov from 2019. That visitor was enriched in CO, not CO2. In many respects, it resembled typical solar system comets, simply with extra carbon monoxide. Atlas's emphasis on CO2 marks uncharted ground. It deviates from familiar chemical patterns, hinting at a distinct birthplace, thermal evolution, or a combination thereof. This is thrilling, as it implies that each interstellar find bears a unique chemical signature, letting us glimpse varied planetary setups throughout the galaxy. At the same time, It complicates efforts to define a standard profile for such wanderers. Key things to monitor at perihelion. The comet will hit its nearest solar approach around October 29th to 30th, 2025, at approximately 1.36 to 1.4 astronomical units. That's within Earth's orbital path, but only just. If water ice lurks beneath a CO2-laden exterior and simply hasn't heated up enough to vaporize, the closest pass could shift the balance. Deeper solar heating should trigger water release. In that case, the CO2-to-water ratio ought to plummet sharply. But if CO2 retains dominance right at perihelion, we're dealing with truly atypical makeup beyond mere heating quirks. Let me toss out a few hypothetical notions up front, emphasizing these are just speculations, not settled views. They're provocative hypotheticals, not established findings. Might Atlas have coalesced in a carbon-laden disk orbiting an aged star? Could it have solidified within a CO2-boosted cloud after a nova event? Or perhaps it hails from a red dwarf's domain, where the snow line hugs closer and gas behaviors tilt differently. Each idea holds abstract merit, yet the available evidence doesn't favor one. Lacking isotope data, no deuterium to hydrogen or carbon-13 to carbon-12 ratios to pinpoint the birth conditions, we're stuck with the coma chemistry as our main hint. It's a lead, but no full answer. The real twist comes when blending this with the motion patterns, that slim disk trajectory. It allows us to roughly map a source we can't follow orbitally. The thin disk path implies a fairly youthful, metal-abundant setting. The CO2 prominence evokes frigid assembly conditions. Merging them suggests an equivalent to a far-off Kuiper belt in some other stellar realm, likely with a volatile blend unlike our own. That's not quite the end of it. It's not the ultimate explanation, but it offers a solid structure, and that's a step up from what we knew before Webb's observations. The coma does seem peculiar, no doubt, but it's far from the only unusual feature. When researchers directed polarimeters toward 3I, examining the way light bounces off the particles in the coma, they uncovered something that doesn't merely stand out from typical comets. It defies everything observed across the solar system. The particles surrounding Atlas behave in ways that dust simply shouldn't. Part 4. The polarization oddity. Polarimetry might come across as an obscure method at first, but its insights are incredibly revealing. As sunlight interacts with dust particles, it disperses. A portion of this dispersed light polarizes, with the electric field vibrating more in a particular direction instead of scattering randomly. The extent of that polarization, along with its variation based on the angle connecting the sun, the particles, and the viewer, reveals details about the dust's characteristics. Things like particle dimensions, forms, density, and make up all imprint distinct patterns on the polarization graph. For years, scientists have recorded polarization data from asteroids and comets, compiling a catalog of standard solar system dust behaviors. Atlas bucks that trend entirely. Initial polarimetric readings from the Very Large Telescope, the Nordic Optical Telescope, and the Rosen Observatory, captured at phase angles ranging from 7 to 22.4 degree, revealed a profound, slender negative polarization peak. Let me break this down. Negative polarization indicates a drop below zero at low phase angles, a trait observed in certain solar system objects, though typically it's mild and wide-ranging. For Atlas, this negative peak plunges to around -2.7% near 7 degrees, then flips and returns to positive values by about 17 degrees. That mix of depth and narrowness is entirely new to us. No comet has shown it. No asteroid either. It wasn't present in 2I/Borisov, the last interstellar visitor. Why does this stand out so much? I'll spell it out simply. At angles approaching backscattering, those near the direct line from the sun to the observer, light reflection can yield quirky results. Processes like coherent backscattering or shadow concealment might cause polarization to dip negative. Yet the severity and span of that dip hinge on the particle's traits. Loose clusters of small building blocks usually generate milder, wider negative peaks. Denser particles yield other patterns. Density plays a key role. Layers of organic materials or frost influence the outcomes. Atlas's polarization profile shouts that its particles feature a microstructure unlike any we're familiar with. So what might cause such a sharp, intense negative peak. Consider these options. Loose clusters with a precise range of sizes. Dense particles boasting atypical light-bending qualities. High-density particles arranged in self-similar fractal patterns. Surfaces coated in frost or organics that alter reflection traits. Or even magnetic elements shaping how particles clump in the coma, though that's more of a hypothesis. The key takeaway: various setups of physical traits can yield comparable polarization marks. Thus, you can't pinpoint the exact particle makeup from polarization data by itself, but you can eliminate certain ideas. And clearly, whatever forms Atlas's dust, it doesn't match the usual loose cluster model that fits most comets. Comparing with additional observations strengthens the case. Webb's spectral analysis detected water ice signatures, aligning with frosty particles. Color assessments, projected to low phase angles, point to a reddish exterior akin to some distant Kuiper belt objects and centaurs such as Pholus. Reddish hues often signal organic compounds or bombarded ices. Piecing this together paints a compelling image: reddish particles, frosty makeup, bizarre polarization. Combined, it suggests Atlas's dust reflects particle formation and clumping under unfamiliar conditions, perhaps from a planetary setup with distinct environmental factors compared to our own. Now, I'll touch on a notion that's circulated in scientific discussions and online forums, and I must emphasize this strongly. A few have pondered artificial particle designs. The concept that this polarization could, theoretically, be crafted intentionally by tailoring particle sizes, shapes, and materials to achieve a desired reflection effect. I must state plainly, there's zero published, vetted research supporting this. It's purely speculative, more of a thought experiment than a hypothesis. We mention it only because Atlas sparks curiosity about the boundaries of possibility, beyond just likelihoods. That said, the far more plausible account is ordinary dust with rare but natural attributes. Scientifically, this points to something truly intriguing. Atlas's particles could reveal unique particle assembly processes in alien star systems. Particle evolution in young planetary disks relies on factors like heat, atmospheric pressure, and chemical mix. Position, turbulence, and various environmental influences come into play. If the conditions in Atlas's home star system differed from ours, the dust that coalesced there could possess distinct characteristics compared to the material in our solar system. This isn't some bizarre anomaly. It's simply the laws of physics operating under altered circumstances. And that's truly fascinating since it implies that each interstellar object arriving here offers insights into planetary formation processes that are otherwise impossible to examine. The negative polarization aspect is also crucial for developing accurate physical simulations. When researchers attempt to match scattering theories to observational data, they must consider single versus multiple scattering events. They need to select intricate refractive indices. They have to settle on particle size distributions. The observations of Atlas are imposing limits on these options, pushing current frameworks to their limits. Certain groups are developing fractal aggregate approaches with defined monomer dimensions. Others are investigating coded sphere frameworks. The key takeaway is that Atlas is rigorously challenging our grasp of light scattering, which will ultimately refine the models applied to all other scenarios. What to monitor after perihelion? As Atlas approaches smaller phase angles from Earth's viewpoint, additional polarization data will emerge. Will the negative feature migrate? Will the inversion point change? Might we observe hysteresis, where the path away from the sun diverges from the approach? Each of these outcomes would reveal details about dust evolution as the comet ramps up its activity. And if fortune favors us, we could obtain rapid polarimetry readings to detect temporal fluctuations, suggesting insights into rotation or ejection dynamics. Polarization indicates unusual dust traits. Yet dust is merely the byproduct. What are the core driver? What forces are influencing Atlas's body directly? Because this next point ought to raise red flags. Atlas exhibits an active envelope. It's releasing gas and particles. Nevertheless, amid this evident dynamism, we've failed to spot the anticipated signature. There's no observed speedup. Part 5, the absent boost. Let's briefly revisit Oumuamua. When that initial verified interstellar intruder zipped by in 2017, it ignited a frenzy. Not solely due to its extraterrestrial origins, though that was thrilling, but because its path strayed from a strictly gravity-bound trajectory. It sped up slightly, yet detectably. This boost aligned with outgassing, akin to a propulsion from vaporizing frost nudging the body astray. However, Oumuamua lacked a detectable envelope, no gases, no grains, at least nothing visible to us. Thus, an unexplained surge without overt signs fueled endless theories. A few grounded in science, probing dim ices or unconventional volatiles. Others veered into less rigorous territory, like solar sails or extraterrestrial artifacts. Now compare it to I/Borisov. Borisov sported a prominent, straightforward, predictable coma, complete with non-gravitational propulsion. Precisely as anticipated. Gas emissions imparting thrust to the core, altering its path. Classic comet mechanics from the playbook. Borisov was unremarkable in the most reassuring manner. It validated that visitors from beyond can mimic our local icy wanderers. Turn now to 3I. Active envelope, confirmed. CO2 emissions, yes. Dust ejection, active. Non-gravitational propulsion evident in positional data? No, not in the most recent analyses. That's puzzling. Outgassing typically triggers a thruster-like response. The expelled gas imparts momentum. As it departs the surface, it recoils against the core. This recoil typically alters the trajectory in foreseeable patterns, quantified by A1, A2, and A3 parameters in the conventional non-gravitational dynamics framework. Those signatures aren't appearing in Atlas's path, at minimum not so far. What's the reason? Several explanations. 1. Configuration. Should the outflows be evenly spread across the core, the impulses might neutralize each other. Picture minuscule engines blasting uniformly in every direction, overall thrust nullified. This could occur if the core is tumbling or if evaporation arises from balanced, opposing zones. 2. Rotation dynamics. If Atlas spins in a fashion that evens out outflow orientations across its cycle, the cumulative boost might fall beneath measurable thresholds. 3. Heft. A larger, denser core would diminish the impact of individual jets. Hubble's maximum estimate for the core diameter stands at roughly 5.6 kilometers. Should Atlas lean toward the upper bound and boast high density, those extra gravitational influences could exist but remain too subtle for current detection. 4. And here's the intriguing part. CO2 versus H2O, with CO2 prevailing at $3 Australian dollars. CO2 vaporizes more uniformly than water owing to its higher volatility. It doesn't require concentrated solar heating to release. Water, conversely, often produces targeted streams, particularly from concentrated hotspots. If Atlas's current output at this range stems predominantly from CO2, and if that venting proceeds somewhat evenly, it might account for the weak non-gravitational indication. The real proof will arrive at closest solar approach. If water activates and begins releasing uneven in terms of measurements, we'd expect those A1 and A2 components to show up in the orbital calculations. Allow me to toss out a bit of conjecture here, and I'll mark it plainly as a storytelling tool rather than any factual assertion. The concept of inertial damping pops up often in sci-fi tales. It suggests a system that counters sudden movements to maintain equilibrium. Might 3I's thick, shielded exterior combined with its balanced CO2 emissions create the illusion of deliberate steadiness? Could it seem to a distant viewer as if it's defying the typical erratic motion of comets? The short answer is probably not. Everyday natural phenomena account for the observations without issue. Yet the mere possibility of posing such a query, the way Atlas's actions stand out enough to spark curiosity, speaks volumes. What signs should we monitor as it nears perihelion? Should water activity increase and the jets turn uneven, non-gravitational effects ought to emerge in the positional data. If those effects materialize and align with standard comet emissions, perfect, we've cracked the puzzle. But if they fail to show, if Atlas displays ongoing signs of activity minus any detectable push, we'd enter genuinely bizarre territory. That scenario would point to either an oddly precise rotational setup or some unknown aspect of its core makeup. Why does any of this count? On a hands-on level, if Atlas's path remains forecastable without major non-gravitational shifts, organizing flyby operations gets simpler. No need to fret over the target veering off course. It might seem basic, but far from it. Planners require certainty on an object's position long into the future. Erratic comets make poor objectives. Dependable, steady interstellar travelers rank high for close encounters or potential retrieval efforts down the line. Thus, we have an entity that's compositionally odd, visually peculiar, and emotionally strange. But there's more to unpack, dipping into themes of chance and spatial arrangement. Plot Atlas's origin point across the heavens, examine its incoming trajectory before solar pull altered it, and something unsettles folks. Not experts, mind you. Researchers grasp biases in data and probabilities, but everyday observers, online commentators, those drawn to shapes and pondering their significance, they're the ones buzzing. So, let's delve into the setup of happenstance. Section 6. The setup of happenstance. Each interstellar visitor boasts a radiant, a spot on the dome of the sky indicating its approach vector prior to the sun's tug warping the route. Picture it as an inverted perspective line. From beyond our system, spotting Atlas inbound. It originates from one fixed angle in the cosmos. That angle mapped onto the star map becomes the radiant. For 3i, this radiant occupies a spot tied to the Milky Way's disk and the solar apex, the path our star carves through the neighborhood rest frame. Simulations indicate the following. The Otterhigh-Oxford simulation, which generates interstellar object populations from planetary ejections, forecasts a spread of velocities and origins. The bulk hail from flat-orbiting stars akin to ours in the galaxy's layer. Yet due to the randomness of planetary toss-outs, stellar close calls, and orbital disruptions flinging items at rapid paces, a fast-moving fringe exists in the spread. Atlas's pace, roughly 58 kilometers per second against the sun, plus its radiant bearing, fits snugly into projections for hurled items from such stars. Models don't flag it as extreme. It's distinctive, sure, but inside the anticipated bounds. Perez-Cuto's motion analyses concur. Atlas matches thin disk traits even with its substantial odd speed. The mix-up stems from peculiar velocity. It evokes mystery, as if the thing's acting out of turn. In reality, peculiar velocity simply denotes motion against the local rest frame. It's jargon, not critique. Ancient stars carry hefty, peculiar velocities from eons of gravitational jostles. Atlas's path aligns with that pattern. No thick disk drifter or halo intruder here. Just a disk-borne piece with a past of orbital turbulence. So what fuels the chatter on alignments? Why do weblogs and discussion threads hype solar apex overlaps or orbital close approaches with bated breath? Because we're wired to hunt for designs. We note Atlas skimming past Mars at around 29 to 30 million kilometers. And it feels exact. We spot its entry angle and superimpose it over Earth's path, Jupiter's loop, or Voyager's route, spotting chart lines that appear deliberate. But consider this. Charts deceive, not on purpose, but through distortion. Compressing 3D vastness into a 2D projection makes distant elements seem proximate. It all comes down to alignment. But failing to factor in the amount of sky observed and the density of those observations can trick you into thinking any odd path is extraordinary. Bias in selection hits hard. The telescopes conducting these surveys don't sweep the entire heavens evenly. They leave footprints, zones they revisit often and probe more thoroughly. The Atlas survey, which spotted those three eye-catchers, follows a specific pattern designed to hunt near-Earth asteroids. When your observations tilt toward particular angles at certain moments, you're bound to detect things approaching from those spots. That doesn't signal a real bunching of objects there. It just shows your efforts are focused that way. Then there's the added complexity of galactic features. Stellar associations on the move, streams of stars, zones of fresh star birth. They all introduce unevenness in the spread of possible parent stars for these interstellar sojourners. If the origins of Atlas lie in a patch that's sparsely sampled in our observed region, it could appear more solitary than it truly is. Simulations back this up. When you model populations of these interstellar objects and incorporate actual survey quirks, you end up with those voided wedge shapes. Sky sectors where an interstellar arrival should pop up, but no parent star does. Not due to its absence, but because it's too dim, missing a speed along the line reading, or simply beyond the survey's reach. Atlas could be nestled in such a voided wedge. And should that be the case, the puzzle isn't some cosmic riddle. It's a matter of what we've actually seen. Let me address the chatter that's been swirling around in public chats. That Mars close shave, the Jupiter lineup, slicing through the ecliptic. These are genuine positional truths. Sure, Atlas zipped fairly near Mars. Its path does cut through planetary paths. But orbital dynamics reveals the real story. Every hyperbolic interloper dipping into the inner solar system must pierce the ecliptic somewhere. The planets huddle mostly in that flat. So brushing past one isn't remarkable. It's practically inevitable. Folks bandy about those probability figures. What are the chances? Such math usually overlooks the full scope of possibilities. Pose the query as the odds of this exact route skimming within a set range of Mars on that precise day. And yeah, it seems minuscule. But rephrase it too. What's the likelihood any interstellar find we make comes within reasonable distance of any planet at any point? Suddenly, the figure balloons because you've broadened the scope. Picture this diagram I'd love to display. A celestial chart layered with forecasted density for arrival points of these objects. Shadings deeper where theory suggests higher odds of spotting an interstellar guest from. Paler areas are rarer, though still feasible. Atlas's entry point lands in a middling zone, not the densest, not the sparsest. Layer on the survey's sweep patterns, and it clicks why we detected it. Not from any deliberate aim our way, but since we were peering where such visitors might appear. Regarding that tie-in to the solar apex, our sun drifts through the local standard of rest at roughly 240 kilometers per second, heading toward Hercules. Atlas's incoming speed direction shares some overlap with that drift. But honestly, what's the big deal? Distant stars and flung-out debris from them carry speed spreads that mirror the galaxy's spin and the sun's trek. Some align, others push back, plenty run sideways. Atlas showing partial harmony isn't a sign of intent. It's a clue it's from the galactic plane. Let me stress this. The overlaps that catch eyes, the Mars near miss, the schedule, the incoming angle, they're not trivial. They're intriguing. They spin a captivating tale. Yet intriguing and captivating don't equate to oddball. The fix for worry over flukes is sharper stats and bigger datasets. Once we've logged 10 such interstellar passers-by, we'll tally how many graze planets. With 100, we'll chart the full spread of entry directions. For now, stuck at just 3, we're dealing in stories, not hard numbers. What insights will extra position tracking bring after closest solar approach? A sharper entry point. A tighter read on the approach speed direction. These will narrow down Atlas's sky origins and its pre-solar pace. A big shift in that entry with improved info could dissolve much of the alignment buzz. If it holds steady, we'll pinpoint a clearer aim for later backward traces using upgraded star maps. But velocity goes beyond direction. It's the rate compared to the local standard of rest. And Atlas clocks in fast. Not outrageously so, but quick enough to spark tough inquiries. After all, in the galaxy's speed landscape, trends emerge. Fresh stars lag behind the LSR. Aged ones race ahead. An object's pace reveals in its dynamic lifetime the duration it's endured gravitational jostling. And if you factor in Atlas's pace accurately, if you figure out the time frame required to accumulate that momentum via ordinary mechanisms, the result is disconcerting. Atlas could be far more ancient than you'd guess. Section 7. The prohibited velocity threshold. 58 kilometers per second. That's the speed at which Atlas is approaching, measured against the Sun. Its orbital eccentricity stands at roughly 6.1. Firmly hyperbolic, far from the barely unbound paths of certain long-period comets that slink in from the Oort cloud. Profoundly hyperbolic, clearly of interstellar origin. Yet here's the catch. 58 kilometers per second outpaces the typical inbound speeds of long-period comets, which usually hit the inner solar system between 10 and 30 kilometers per second. Still, it falls within the forecasted limits for interstellar objects hurled from other planetary setups. Certain models of such populations foresee ISOs reaching velocities of 70 or even 80 kilometers per second. Thus, Atlas moves swiftly, but not impossibly so, unless age enters the equation. Estimating age through kinematics is challenging, yet attempts have been made. Hopkins and Taylor-Seligman released projections derived from Atlas's speed profile. Their figures span from around 3 to 11 billion years, varying by the starting assumptions and priors. A separate analysis elevates the minimum to beyond 6 billion years. These aren't dinosaur-era timelines. These timelines stretch back before our solar system's birth. The sun clocks in at 6 billion years. Earth at 5 billion. Should Atlas truly date to 7 billion years, it was drifting through the galaxy, while our solar system remained a swirling nebula of gas and dust. Allow me to break down the reasoning simply. The local standard of rest captures the mean motion of stars near the sun. It embodies the overall drift of the galactic disk. Freshly formed stars, born from homogenized gas, track near the LSR. They lack the exposure for gravitational disruptions. Ancient stars, those that have circled the galaxy many times over, get nudged by nearby stars, gas clouds, and spiral arm passages. Each nudge boosts their speed. Gradually, a star's path drifts away from the LSR. That deviation, the peculiar motion, serves as a timer. Greater deviation correlates with greater age, on average. Atlas's trajectory reveals a substantial deviation from the LSR, implying considerable antiquity. But consider this subtlety. The link between speed, spread, and age isn't straightforward. It's probabilistic. A recent arrival might boast high peculiar motion from an early strong jolt. An elder body could show minimal peculiar motion if it dodged significant disturbances by chance. Thus, claims of Atlas at 7 billion years offer a likelihood drawn from group norms, not a precise gauge. Even accounting for that uncertainty, the estimates lean toward antiquity. So why the talk of a forbidden window? It arises because experts anticipate interstellar objects to display speed patterns akin to local stars, which cluster in a roughly Gaussian halo around the LSR. But that's an oversimplification. Actual speed patterns aren't purely Gaussian. They're lumpy. Stellar associations, streams, and moving clusters introduce irregularities in velocity realms. If Atlas originated from such a group or a scattered cluster, its speed might echo the collective drift of that assembly, rather than solely its personal history. Therefore, the forbidden window concept, that Atlas's velocity exceeds plausible natural origins, falls apart once galactic complexities are factored in. What everyday mechanisms might speed up or slow down an object across eons? Close stellar encounters. Whenever Atlas swung near a star by a few parsecs, it experienced a gravitational pull. Modest pull, yet across billions of years, those accumulate. Gas clouds. Thick interstellar zones can impose resistance or gravitational boosts based on alignment. Galactic gradients. The Milky Way's gravity field varies. Paths within it can absorb or shed energy progressively. Traversing spiral arms. Those density waves shaping the arms can jolt crossing objects. These are all routine, thoroughly mapped phenomena. Over vast spans, they can drive an object's speed to dozens of km/s away from the LSR. Now, permit me to venture a few hypothetical notions. Mark these as creative sparks, not assertions. Might magnetic friction from the interstellar medium gradually break a charged body over billions of years? Theoretically, sure. Though the impact is negligible without plunging through exceptionally dense, highly magnetic zones. Might dealings with an unconventional gravity environment, say, peculiar dark matter or tweaked gravity laws, shift an object's pace absent direct star brushes? That's edge-of-science speculation, lacking observational backing, though it circulates in niche discussions. Might engineered braking, via a propulsion setup sporadically activating across eons to refine the course, account for an apparently calibrated velocity? Why speculate on such wild deceleration theories? It's all guesswork without solid proof, yet it pops up in discussions anyway. Testing these unusual slowdown concepts? Look at spin dynamics. If Atlas has endured outside forces beyond typical gas release, its spin could reveal oddities. Comet torque effects. If plumes are erupting unevenly to curb rather than boost orbital shifts, that's something we can quantify. Look at velocities before and after closest solar approach. If Atlas's pace around the sun deviates from what's expected due to gravity and comet venting, that signals trouble. No such irregularities have turned up yet. So exotic braking remains an answer hunting for a question. This leads into the following section. Rapid motion combined with vast age means losing the trail. If Atlas has roamed for billions of years, The stars it zipped by, and the gravitational tugs it felt number in the uncountable. Every encounter injects uncertainty into its path record. After integrating backward for 10 million years, you're no longer following the true route. Instead, you're following one likely path amid a ballooning swarm of options. The history doesn't simply blur, it dissolves into disorder. Part 8. The history that dissolves. Picture attempting to map a lone stone's journey along a stream bottom after 10 million years of rushing currents. The stone endures. You can grasp it, but its exact path from far upstream to your palm? Erased, swept off by countless minuscule swirling currents, each giving it a minor shove. In theory, the laws of motion run both ways, forward and reverse. Yet the details required to unwind the path, the exact spot and speed of every droplet at every moment, have scattered into disorder. Atlas plays the role of that stone. Our galaxy is the stream, and 10 million years stretches out endlessly. Pereira's group halted their backward simulation at 10 million years since going further renders origin hunting pointless. Two factors explain this. 1. Disorder. Paths of stars and rogue space rocks form unpredictable setups. Tiny errors in starting points amplify wildly over time. At 10 million years, the array of potential routes has ballooned into a vast haze where no single track stands out. It's no longer about calculating the past. It's just generating static. 2. Data constraints. The Gaia mission provides speed measurements toward us for just a portion of stars, mainly the brighter ones closer than a few hundred parsecs. Past roughly 500 parsecs, the coverage plummets. So if Atlas hailed from a system 2 kiloparsecs distant, we'd lack the info to check. 10 million years marks the intersection of data gaps and motion chaos, both urging a halt. Universal forgetfulness isn't a physics flaw. It's baked into how information works. The cosmos doesn't log every path precisely. Details keep getting blurred, blended, surrendered to disorder. An item's backstory persists physically. Cause and effect hold firm. But accessing that backstory, not always possible. After sufficient duration and encounters, the chain of events lingers theoretically, yet becomes impossible to follow practically. Atlas carries a history. It originated somewhere. But the cosmos's record-keeping has torn up the evidence. This extends past just 3i. We're on the cusp of routine finds of such wanderers from beyond our system. The Vera C. Rubin Observatory, once called LSSD, is gearing up. It will scan the full southern heavens every few nights, probing faint targets deeply to spot dim intruders. Projections indicate it might detect scores to hundreds of these cosmic drifters annually when running at peak. Like 3i, most will be ancient, with origins lost to time. Yet a few, the fortunate cases, will be recent escapees. Items that departed their home, star mere hundreds of thousands of years back, at most a million. For them, the forgetting hasn't kicked in. Their path records remain recoverable. Those are the traceable gems. What if superior data emerge for Atlas? Enhanced speed readings for dimmer stars? Upcoming Gaia data drops will extend to fainter objects, though ground and space-based radial velocity measurements face inherent barriers. Imagine future probes like Enhanced Gaias, charting stars to magnitude 10 or beyond with complete position speed profiles in all directions, or detailed charts of the nearby space gas and grit. Knowing the makeup and flow of material along Atlas's former route would refine models of drag and disturbances. But that's all perspective. For the moment, Atlas's backstory fades into the mist. One deeper angle merits a moment's reflection. Underlying forces are real. Atlas got flung from some planetary setup. That launch stemmed from something. The parent star, the trail leading back to where Atlas originated, has been lost, even if the object itself is very much real. Those gravitational forces that molded its trajectory across billions of years, they definitely occurred. That's not up for debate. However, tracing the sequence of events from today's observations can break down. Not due to the events themselves failing to take place, but because the details have become too jumbled to piece together again. It's similar to trying to figure out the exact conditions on a particular day 3 billion years back. The weather occurred, driven by real factors, yet the records have vanished, blended into the random heat of the air, seas, and Earth's surface. Atlas's beginnings have faded just like that. Not wiped out, but beyond salvage. This loops back to its chemical makeup in an interesting way. If dynamic tracking of its path proves impossible, we can still examine its composition. The overwhelming presence of CO2, the distinct polarization signals, and the characteristics of its dust offer hints about its surroundings. They won't reveal the exact location of its birth star, but they indicate the type of region it came from. Chilly, rich in carbon, maybe even ancient. That's valuable insight. Without a clear lineage from its orbit, the elements in it serve as the guiding clues. Let's venture a bit more into informed guesswork. If Atlas is indeed from a bygone era, drifting for 7 to 10 billion years, it would outdate key moments in the galaxy's timeline. The most recent big clash, the Gaia-Enceladus merger, unfolded roughly 10 billion years ago. That smash-up integrated a small galaxy into the Milky Way, disrupting the disk, sparking new stars, and reshaping the galaxy's elemental balance. Should Atlas have formed before then, its makeup might echo a version of the Milky Way that's long gone. It's a stretch, sure, but an exciting one. As I noted before, research like the Gödel gases analysis highlights numerous near misses with stars when running simulations backward, yet their figures clash with those from periscotes. The reasons? Variations in starting points, orbital ambiguities, chosen stars, and simulation techniques. Once you align the approaches, the differences fall into place. Still, the overall agreement holds firm. Regardless of the paper or dataset you consult, the key takeaway remains unchanged. No identified home star, lots of tight encounters, but nothing sufficiently near or leisurely to have real impact. Everyone agrees the history's timeline is a mess. Time has thus muddled the backstory. Backward orbital modeling hits a wall, yet Atlas persists in the present. It stays lively, shrouded in a haze of gas and dust. Humanity's top observatories are trained on it. Hubble, JWST, Earthbound setups. Despite that, an odd quiet lingers, a shortfall of expected measurements. Part of it stems from physical limits, part from practical hurdles. In those voids, though, theories flourish. Part 9, the quiet from the instruments. Hubble observed 3.2 and established a cap on the core's diameter at around 5.6 kilometers. That's no outright sighting. It's an estimate derived from the faint light not attributable to the surrounding glow. The core hides within the brightness of gases and particles. Direct imaging isn't feasible. Instead, you simulate the envelope, remove it, and check the residue. For Atlas, that leftover aligns with a core ranging from roughly 0.32 to 5.6 kilometers, based on guesses about reflectivity and output levels. It might span just hundreds of meters or stretch to kilometers. We're not certain. Bluntly put, what we're missing, and this bears repeating, is radar information. No bounces detected from 3I. The explanation? Radar for minor objects demands proximity and a decent reflective area for pickup, and Atlas has stayed too distant for viable ranging with today's gear. Arecibo, capable of such feats, tumbled down in 2020. Efforts at Goldstone and the Green Bank telescope have targeted others, but Atlas's range and alignment render it unworkable. Thus, no radar returns, no cover-up, merely science and scheduling constraints. Infrared thermal readings add another layer of nuance. JWST's near-infrared tool revealed signatures of gases, ices, and grains, but isolating the core's heat output from the envelope's reflected light and particle glow demands peeling apart overlapping signals. That's tough amid an energetic coma. So, ideas about a sturdy outer layer, spongy build, or oddball features on the nucleus. They're jumping the gun. The evidence isn't solid enough for firm judgments. Reports from ground observatories have flagged odd patterns in brightness over time via photometry. But the catch, the coma obscures the nucleus. You're viewing not just the stone, but stone mingled with gas and dust, all shifting in unison. Pulling apart spin rate, form, and outburst strength from such scattered light proves a real challenge. Teams are tackling it, yet findings stay tentative. Assertions of quirky spin behaviors or off-kilter wobbling remain guesses for now. Allow me to stress once more something crucial to note. Despite the evident activity, no non-gravitational acceleration has shown up in Atlas's path around the Sun. It's a straightforward, uneventful finding. Yet, Even the mundane can feel odd when you dive into the physics of the coma. Typically, lively comets exhibit that kind of acceleration. Atlas hasn't, at least not so far. That's noteworthy. Still, as I mentioned before, there are reasonable explanations. Things like balanced gas releases, CO2 dominance over water ice, or the way it spins could all account for it. The key takeaway? The lack of non-gravitational pull isn't proof of engineered control or strange physics. It's merely a curious observation that could clarify with additional measurements from the sky. Shifting gears to media coverage versus scientific publications. Sensational stories about city-sized structures, stunning snapshots from the Mars encounter, flashy renderings. They're out there. Such pieces spark interest and draw people into the narrative. However, if you stick to official releases from NASA, the Hubble Space Telescope, and James Webb, the scientific tone stays far more restrained. The core size remains debatable. The surrounding haze is heavy on CO2. The light polarization stands out as atypical. That's the essence of what the research papers report. The disconnect between flashy news and solid evidence is where misunderstandings take root. The close approach to Mars occurred from September 29th through 30th, 2025. Atlas passed by at roughly 29 to 30 million kilometers, or about 18 million miles. Not exactly a razor-thin skim of the planet's air, but an ideal setup for spacecraft already circling Mars. Europe's Mars Express, NASA's MAVEN probe, and even the surface rovers with their lenses all got prime views from angles unavailable from our home planet. With observations from various positions, scientists could refine their mapping of the coma's shape, narrow down the directions of gas emissions, and perhaps spot subtle details hidden from Earth-based telescopes. Thus, the Mars event proved highly useful for research, even without the blockbuster drama. Now, I have to tackle a rumor circulating on the web. Allegations of hidden spectral data, buried findings, suggestions that research groups are sitting on bizarre results they're reluctant to share. Let me state this plainly. Major observatory projects follow established data handling processes. From initial captures to refined readings and final analyses, it all unfolds over several months. Expert scrutiny adds more delay. There's also a grace period for the proposing teams to work through their data privately before going public. This is just how the field operates. Not seeing a graph right away doesn't signal a cover-up. It's a sign of methodical progress. If you're pushing for instant data drops, push for better open data rules and faster processing tools. But don't mix up routine procedures with shadowy plots. Looking ahead to upcoming findings, what to keep an eye on. Gas composition at closest solar approach. Will CO2 continue to lead, or will water vapor surge? Estimates of the nucleus after perihelion. As the coma shifts, subtracting its glow could yield sharper limits on the rocky core. Terms for non-gravitational forces in orbital models. Should A1 and A2 factors emerge post-perihelion, it would indicate water-driven thrusts activating. Detailed spectral scans with strong signals. A high-quality readout might reveal minor elements, like deuterium levels in hydrogen, carbon isotope ratios, or sulfur traces. Those details would offer clues about where and how it formed. The instruments aren't quiet due to some cover-up. They're quiet because capturing this stuff is tough, the comet's distant, and the analysis chain moves deliberately. I get that it's frustrating, but it's the truthful side of things. And truth is what distinguishes real inquiry from mere tales. That said, while on the topic of tales, there's a massive issue we've been skirting. The cultural clash in astronomy circles. The discussion that's less about the evidence itself and more about how we read it, how it's portrayed, and the implications of labeling something as manufactured. Part 10, the scholarly chill. I'll outline the scene as fairly as possible. The bulk of the astronomy world, the groups issuing papers, reviewing submissions, operating the scopes, they describe Atlas as a typical interstellar comet with quirky features. Rich in CO2, blazing along at odd speeds, showing bizarre light scattering, origin unclear, yet all fitting within normal cosmic rules. But a smaller viewpoint, led notably by Avi Loeb and his Harvard colleagues, promotes the idea of technological relics, not as ironclad assertions, at least not in formal channels, but as intriguing options deserving exploration. This shift in emphasis has sparked division. Loeb's key ideas, pulled from his online writings and articles, Cover topics like alignments with the ecliptic plane and planets, efficient near misses, polarization possibly hinting at signals, or even speculation on nickel-heavy makeup without iron, though the latter lacks broad expert backing. The reasoning unfolds roughly like this. Tally the chances of Atlas's route just happening to swing by Mars and Earth in ways perfect for scrutiny, and the figures seem slim. Factor in the peculiar makeup and light effects, and the likelihood of it all being purely natural shrinks more. Eventually, Loeb suggests, it's time to weigh the other pos. Look, it's clear that Atlas isn't some comet. It's a spacecraft, a remnant, an engineered object. The backlash from the scientific community has come fast and sharp. Experts like Jason Wright, who leads the Penn State Extraterrestrial Intelligence Center, have taken apart the approach. They argue that selection biases aren't getting the attention they deserve. Framing the chances of a hawkish post-discovery scenario, figuring out probabilities once the evidence is already in, is a textbook stats blunder. Then there are the media drivers. Buzz about artificial origins draws clicks, grants, and spotlight, pushing folks to amplify guesses instead of sticking to the facts. Wright and his peers have penned detailed pieces explaining how slim odds don't equal impossibility, and how bold assertions demand solid proof, not flashy announcements. Why should these labels count so much? They steer the money. Labeling Atlas an interstellar wanderer funnels it into planetary research budgets. Calling it a possible tech artifact shifts it to SETI efforts, or ramps up national security reviews, or pulls in cash from philanthropists hooked on big-picture mysteries. Project pitches evolve, institutional caution levels adjust. The James Webb Space Telescope didn't aim at it thinking it could be a vessel. It targeted Atlas assuming it's an interstellar comet, perfect for analyzing icy compounds. But if the story pivots, upcoming observations could get a different rationale. And that cycle linking stories to funding decisions turns this into way more than a scholarly spat. There's a telling precedent with Oumuamua back in 2017. No obvious dusty tail plus odd non-gravitational push fueled wild theories. Avi Loeb co-wrote a study probing light sail ideas, imagined lightweight mirrors driven by sunlight pressure. The work held up as a solid dive into possibilities. Yet news stories and follow-up blogs blew it up beyond mere hypothesis. Views among the public tilted. When 2I/Borisov showed up and acted like your standard comet, the impact lingered. Folks started seeing interstellar visitors as possibly man-made until evidence proved otherwise. Atlas picked up that extra weight. How does the landscape differ from Oumuamua to this 3I candidate? Smarter initial reporting. JWST is online now, capable of decoding chemical makeup in ways 2017 couldn't touch. Earth-based polarization studies have sharpened. Position measurements are more precise. So the info flow for Atlas is denser, quicker, and finer-grained. That ought to clarify the natural or made debate sooner. Still, it hands both camps extra bits to cherry-pick. For this piece, my take is straightforward. Treat guesses as guesses. Distinguish personal posts from peer-reviewed findings. Push for experiments that could debunk either the everyday or the exotic angles. After all, the real risk isn't chasing a quirky notion and learning its bunk. The danger is ignoring it and overlooking something genuine. Science thrives on scrutiny, not suppression. So what checks can we run? Consistent polarization scans over various lighting angles. If the weird negative signal stems from unusual particle traits, it should repeat and fit models. If it's a one-off or setup glitch from initial views, it'll shift. Changes in gas mix as it nears the sun. Regular comets follow expected patterns when heating up. Any big swing from Atlas would raise eyebrows. After closest solar approach, checks for non-gravity motion models. If acceleration factors A1 and A2 show up and align with gas jets, the natural case strengthens. If they vanish amid heavy venting or emerge with strange patterns, that's a head-scratcher. Detailed, high-quality spectral scans for unusual elements. Claims of nickel sands iron demand the raw data, peer-checked, with uncertainties noted. Without that, it's just talk, not evidence. Staying sharp on media is key. If odds for Atlas's path get pegged at 1 in a million, probe the full scope of what's being scanned. That rarity impresses less when you're sifting through a million options. If a trait gets called never seen before, question the baseline and dataset. 3 interstellar finds don't make a solid stats base. And when Occam's razor gets name-dropped, recall it doesn't crown the easiest answer king. It warns against adding needless complications. Plenty of earthly reasons fit Atlas. They're intricate, sure, but they cover the ground. Made by aliens, tales stack on extras, advanced societies, space voyages, aimed encounters. Those extras call for stronger backing than it seems off. Positively, even out there thoughts drive real work. If an artificial angle secures JWST slots or sparks fresh polarization runs, and the results confirm it's ordinary, yet uncover fresh insights. If the unconventional hypothesis about comet dynamics started to click, that out-there concept turned out to be spot on. The antidote to hasty opinions isn't keeping quiet. It's gathering superior information, refined details. Evidence that narrows down the options until just a single interpretation remains viable. So, assuming Atlas stems from natural origins, which explanations hold up? What narratives align with the composition, the alignment patterns, the motion profiles, and the mysterious background? That's our next stop. After all, natural origins don't equate to dullness. They can be timeless, otherworldly, and profoundly bizarre. And certain explanations for Atlas, in their unique fashion, prove just as astonishing as any engineered construct. Part 11. The Elusive Theories. I'll guide you through a few possibilities that might generate something like Atlas sans any design intervention. These represent viable ideas, not ironclad conclusions. Each matches certain observations. None captures the full picture flawlessly. But that's fine. Science advances through probing ideas against evidence, not by holding out for a flawless concept to drop from above. Theory 1. Leftover remnants from galactic collisions. Our galaxy, the Milky Way, boasts a turbulent past. It's swallowed up lesser galaxies. Gaia, Enceladus, the Sagittarius dwarf, and more are still under study. During a dwarf galaxy's integration with the Milky Way, it's not merely stars that get scattered. Everything follows. Gases, particles, worlds, minor objects. Portions of that material swirl into the Milky Way's outer envelope. Others integrate into the central plane. Should Atlas be a piece from one of those long-ago unions, it might have roamed for eons, cast out from its original setup, well before the Milky Way assumed its present form. This accounts for the ancient motion history. It clarifies the absence of a traceable nearby stellar link. Plus, if the dwarf galaxy featured distinct metal content or volatile makeup compared to the Milky Way, that could justify the prevalence of CO2. Plausible? Absolutely. Verifiable? Not yet, based on available info. Theory 2. Interstellar Wanderer Collision Breakup. Picture a super-Earth or mini-Neptune hurled from its solar setup. It drifts through open space for countless years. Eventually, it swings near a star, not near enough for orbit, but sufficient for gravitational pulls to strain the surface. The shell cracks, fragments split away. Among them, bits laden with CO2 if the inner layers lean toward carbon dioxide frosts. Those pieces evolve into rogue comets between stars. Atlas might represent such a fragment. This fits a potentially sizable, compact core matching Hubble's top estimate of 5.6 kilometers. It rationalizes the odd makeup, though it's conjectural. There's zero straightforward proof of ejected worlds fracturing by stars. It's a reasonable process, unverified as of now. Theory 3. Expulsions after the primary star phase. As a star exits its stable core burning stage, expanding into a red giant or losing material as a white dwarf, its surrounding worlds get reshuffled. Paths become chaotic. Certain planets plunge inward, others get flung outward. Trapped substances in the distant zones can shift around. If Atlas got launched in a late star evolution period, it could have picked up atypical volatile balances via heat treatment in the red giant era. CO2 might amplify if carbon and oxygen were plentiful in the star's envelope and blended into the scattered remnants. This theory covers the advanced age, the elusive source if the host star has dimmed to a white dwarf, and the peculiar composition. Still, it's a possibility, not a certainty. Theory 4. Formation from dense gas cloud remnants, shadowy comets. This is an offbeat notion, not broadly embraced, but deserving a nod. The concept suggests that tiny objects, short of full planets, can assemble straight in thick molecular cloud threads without a star or disk forming up front. These would derive from early stellar seeds, minuscule frozen spheres that solidify in the chilliest, packed areas, then scatter when the cloud breaks apart from close-by star birth or blast waves from supernovae. If Atlas arose this way, its makeup would mirror the cloud's conditions, potentially heavy on CO2 based on carbon and oxygen levels there. Yet this process relies on simulations and sparks debate. The consensus among experts favors a formative disk for small bodies, beyond a mere cloud. Thus, it's tentative, even among these ghostly ideas. Theory 5. Snag then freed in the Milky Way's outer shell. Suppose Atlas doesn't hail from the main plane? Perhaps it's a spacefarer from beyond galaxies, pulled into the Milky Way's gravitational field eons back, circling the envelope for millennia, and only lately plunging inward from some jolt. This would justify its current motion matching the slim disk, yet lacking a hometown tie. It addresses the vintage timeline. Tracing envelope paths across vast eras is tough, but the idea stands on solid conceptual ground. The composition would hinge on its birth site, maybe a companion galaxy, or even void spaces, if that's feasible. How do these ideas measure up against Atlas's observations show a CO2 to water ratio of 7? 6. Scenarios 2 and 3 could account for this via the makeup of the mantle or alterations after the main sequence phase. Scenario 1 hinges on the chemical makeup of a dwarf galaxy. Scenario 4 relies on the chemistry within a molecular cloud. Scenario 5 represents an outlier with its extreme negative polarization pathway. Every scenario accommodates atypical dust properties, assuming the birth setting or evolutionary path deviated from solar system standards. There's no sign of non-gravitational forces even with signs of activity. All scenarios align with this, provided the core is sufficiently hefty or the emissions are evenly balanced. Regarding the thin disk's motion patterns, scenarios 1 and 5 struggle the most here without calling on tailored capture or migration events. Scenarios 2, 3, and 4 more readily position Atlas within the disk. Thus, we might tentatively order their likelihood. Scenarios 2 and 3, fragments from rogue planets or ejections following the main sequence, match the bulk of the evidence using the least unusual premises. Scenario 1, remnants from an early merger, aligns with the timeline and motion but demands particular chemical conditions. Scenario 4, aggregates from molecular clouds, remains highly conjectural. Scenario 5, a capture from the halo, sparks intrigue conceptually, yet proves challenging to verify. Which upcoming observations might challenge these ideas? The distribution of dust particle sizes via photometry beyond perihelion. By gauging how luminosity diminishes over distance, we could deduce grain dimensions, shedding light on the coagulation timeline. Ratios of volatile isotopes, like deuterium to hydrogen, carbon, 13 to carbon, 12, and nitrogen, 15 to nitrogen, 14, would reveal the temperature and chemical signatures of the origin site. High-resolution imaging to spot any breakup. Should Atlas begin losing fragments as it heats, that would reveal its internal strength, linking back to its formative past. These are tough feats to pull off, but feasible. The key insight? Several organic routes could lead to an object that's CO-heavy, aged, and hard to trace. Explaining 3-2 doesn't require artificial intervention. It simply calls for recognizing that interstellar wanderers might arise from natal conditions and orbital tails beyond our current grasp. And that's thrilling, as each such visitor serves as a dispatch from galactic realms otherwise inaccessible. Now, let's push this idea ahead. Suppose Atlas isn't merely aged. What if it's primordial? What if it outdates not only our solar system, but the Milky Way's present form? Imagine Atlas as a cosmic interloper, a survivor from the universe's dawn of stars and worlds. Part 12, the cosmic interloper. Between 3 and 11 billion years. That's the age bracket derived from Atlas's trajectory. The younger boundary already surpasses the sun's vintage. The higher boundary ranks it among the most ancient solid entities we've detected. For context, the cosmos clocks in at roughly 13.8 billion years. The Milky Way's disk started assembling about 10 to 12 billion years back. Should Atlas sit at the upper age limit, it emerged during the galaxy's infancy, amid scant metallicity, as initial planetary arrays coalesced around population 2 stars. A crucial caveat: these age figures are derived statistically, not through direct assay. We deduce them from velocity scattering, how Atlas's path has randomized against the local rest frame. This yields a likelihood-based age drawing from demographic simulations. It's no carbon dating precision, nor a figure etched with decimal certainty. Yet, despite the fuzziness and margins of error, the results tilt toward antiquity that feels unsettlingly profound. Surpassing the solar system's span isn't mere fancy, it's credible. So, I'll pose a hypothetical query, flagged firmly as exploratory musing. Might Atlas count among the galaxy's inaugural solid forms? Could it stem from a premier generation planetesimal in a metal-scarce setup? The earliest stars, born in the galaxy's opening billion years, featured diminished iron, silicon, and other hefty elements tied to stony worlds. Still, they possessed oxygen and carbon from primordial nucleosynthesis and initial stellar blasts. A system orbiting a metal-poor star could exhibit altered composition, higher proportions of ices to minerals, elevated carbon-oxygen mixes, greater CO2 against silicates. Such traits might underpin Atlas's profile if it's genuinely from eons past. The snag? We lack the evidence to probe this. Isotopic signatures would clinch it. Deuterium to hydrogen ratios establish in Big Bang nucleosynthesis, but shift via stellar influences and site-specific reactions. Carbon, 13 to carbon, 12, oxygen, 18 to oxygen, 16. These map the thermal and reactive milieu at birth. Deviations from solar norms would signal a chemically alien origin, but those readings remain elusive. JWST's spectral capabilities excel, yet fall short here. You'd require ultra-precise resolution. Spectral resolution and signal-to-noise ratio are key to extracting those isotope signatures. Perhaps after perihelion, as the coma flares up brighter, somebody might give it a shot. For the moment, though, it's just on the wish list. Let me offer a quick, straightforward rundown on why isotopes are a big deal. Big Bang nucleosynthesis churned out hydrogen, helium, some lithium, and a smidge of deuterium. All the heavier stuff originated in stars. As stars fuse hydrogen to helium, then helium to carbon, carbon to oxygen, they generate particular isotope mixes based on the heat and pressure inside. When supernovae burst, they hurl those isotopes into the interstellar medium. Fresh stars emerge from that enriched material. Planets coalesce from the remaining disk. The isotope proportions in those planets mirror the makeup of the gas cloud where they originated. Measuring isotopes in a comet is like decoding the chemical fingerprint of its birthplace. Comets in our solar system generally show solar-like isotope ratios since they arose from the same cloud as the Sun. If Atlas displays non-solar ratios, it must have come from somewhere else. And if those match conditions from the low metallicity early galaxy, it's essentially a timestamp. Now, connecting this to the galaxy's past. The Milky Way's disk has layers. We inhabit the thin disk, packed with fairly young, metal-rich stars. Then there's the thick disk, ancient and metal-poor, featuring stars with wider velocity spreads. The halo is the oldest, even more metal-poor, brimming with stars from the galaxy's infancy and swallowed up dwarf galaxies. Atlas's motion points to the thin disk, yet it has a hefty, peculiar velocity that nudges it toward the thin-thick divide. That's typical for aged items. Across billions of years, gravity's churn can fuzz the boundaries between groups. Kinematically, then, Atlas might be a thick disk relic kicked into thin disk paths, or an old, thin disk resident that's racked up plenty of speed boosts. Motion by itself doesn't pinpoint it. But layer in the chemistry, the CO2 prevalence and odd dust, and options start shrinking. Thick disk and halo stars usually run metal poor. If Atlas arose in such a sparse metal setting, that could explain favoring CO2 over silicate dust, with fewer rocky ingredients around. Pure speculation, sure, but a lead worth chasing. If we confirm Atlas predates the solar system, how does that reshape our stories? It expands them wide. We tend to view comets as homegrown solar system holdovers from our sun's birth. Interstellar visitors are outsiders, granted, but we picture them as rough contemporaries, born near stars of comparable vintage in the broader sweep of galactic evolution. An ultra-ancient interstellar arrival appends that it's no equal, it's a senior. It roamed the galaxy back when the molecular cloud destined for our solar system hadn't begun to contract. It observed star births lost to us forever. It bears chemical traces from a galactic phase we deduce only from ancient starlight spectra. That's a humbling perspective. Still, a word of warning. Avoid hype about pre-galactic origins. No evidence supports Atlas forming before the Milky Way took shape. Galaxies dotted the universe by then anyway. So, it's a product of the galaxy, not some pre-dawn artifact. Frame the speculation as whether it's older than the typical galactic features we encounter, not whether it outdates galaxies themselves. Stay realistic. Imagine a graphic I'd love to display, a timeline. Kick off at the Big Bang, 8 billion years back. Note the first stars popping up a few 100 million years post-Big Bang. Pin the Milky Way's halo formation around 12 billion years ago. Slot the thick disk at 10 to 12 billion years. Place the thin disk at 8 to 10 billion years. Hit the Sun at 6 billion years. Now slot an Atlas, complete with uncertainty margins. The bottom edge lands near 7 billion years. The top stretches beyond 10 billion. Atlas bridges the span from the Sun's debut to the galaxy's formative years. It's a time vault with a faded inscription. What draws crowds to this angle? It reframes the thing entirely. No longer merely a comet. It's a dispatch in a vessel from profound antiquity. It's concrete proof the galaxy brims with ancient tales beyond our grasp. It links the vague idea of cosmic timescales to a real, observable entity you can aim scopes at. That link, that feeling of bridging eons to graze something real, it's profound. Yet the story pivots here. If Atlas isn't beaming signals, if it's silent on radio or laser fronts, might it still transport data? Could it embed info not through emissions, but in its makeup, its elements, its light polarization? That's the foundation for the following concept. Pure speculation, no doubt, but compelling enough to probe, not for high odds, but because we can test it. Part 13. The Concealed Co-Communications Theory. I'll clarify expectations from the outset. The whole discussion here is purely hypothetical. No peer-reviewed studies confirm that Atlas is artificial, nor is there any evidence indicating it's a communication tool. What's presented below is merely a conceptual exercise, an exploration of how information could potentially be embedded in a non-transmitting object and the methods required to identify such embedding. This ventures into science fiction-like ideas, yet it's anchored in established physics and actual detection methods. View it as an intellectual challenge, not a factual assertion. The notion of non-transmitting intelligence has long circulated in SETI communities. Conventional SETI searches focus on electromagnetic emissions, such as radio waves or optical signals from intentional broadcasts. However, an alternative perspective examines inert objects that store data within their physical form rather than emitting it. Imagine a spacecraft that imprints its intended function through how it disperses light, the reflective properties of its exterior, or the configuration of its path. No energy source would be required, nor any electronic components. Just precise engineering and an observer alert enough to spot the clues. One way to conceal data might involve polarization. This property arises from factors like particle dimensions, forms, density, makeup, and the angle of dispersion. By manipulating the microscopic arrangement of dust particles, it's theoretically possible to craft a polarization profile with deliberate characteristics, a notch at a particular orientation, a reversal at another, or alterations in amplitude or breadth tied to light wavelengths. To casual eyes, it would resemble ordinary dust. But to someone primed to search for anomalies, it could reveal embedded details. Such details might include positional data, a time marker, or an identifier. The key difficulty lies in separating intentional patterns from random environmental fluctuations. Atlas displays a pronounced, slender negative spike in its polarization profile near a 7 degrees phase angle, flipping positive around 17 degrees. Does this suggest deliberate construction, or is it just particulate matter? Most likely the latter. Standard dispersion processes account for it without needing to posit hidden messages. Still, in this speculative framework, detecting encoded signals in that profile would demand frequent polarization measurements across diverse wavelengths and angles. Researchers would seek irregularities from idealized curves, abrupt traits mismatched to typical particle setups, or repeating oscillations linked to rotation or orbital position. So far, nothing like that has emerged for Oumuamua. Its polarization stands out as atypical, yet it aligns reliably with unconventional but plausible dust simulations. Could antitails and dust streams serve as encoded markers? Occasionally, comets develop antitails, subtle tails directed sunward instead of outward, due to sizable particles in unique orbital setups. If an entity could regulate the release of dust in terms of schedule and orientation, patterns might form. Intensity plotted against direction, luminosity over duration, or a series of bursts. Spotting these would require detailed, time-lapsed images with fine detail. One would track the evolving envelope over spans of hours or days, hunting for formations that defy fluid dynamics simulations. Once more, no such findings exist for Oumuamua. The envelope shows irregularity and solar side intensification, which is typical of thermal effects from the star. No markers, no progression. In the broader SETI landscape, quiet probes, often termed Bracewell probes, represent a long-standing hypothesis. These envision advanced societies dispatching scouts that remain dormant, scanning for signs of sapience before activating transmissions. They hover undetected, surveil quietly, and bide their time. Should Atlas qualify as one, it would currently operate in stealth mode, monitoring and logging without output. Testing this would involve probing for reactions, directing signals its way to elicit a reply, scanning for path deviations unexplained by gravity or thrust, or tracking exotic outputs like high-energy photons or particles unrelated to cometary processes. To date, all checks have yielded silence. What empirical observations could probe for hidden data? Comprehensive polarization scans in visible light, near-infrared, and mid-infrared bands to detect if spectral traits align unnaturally. Precise timing of light measurements to uncover rhythmic luminosity shifts suggestive of digital codes. Compositional analysis of dust for spectral signatures of atypical substances in solar system bodies, unweathered metals, or intricate organic compounds beyond natural norms. Even passive radio surveillance as a precaution. These approaches are all within current capabilities, and several have been attempted. No irregularities have surfaced. Where does the encoding hypothesis probably break down? Occam's principle favors simplicity. Everyday dispersion covers Atlas's polarization quirks. Routine cometary venting accounts for the envelope. Standard gravitational mechanics justify its course. There's no call for artificial origins. The onus falls on proponents of exotic interpretations to demonstrate features defying natural origins. Atlas lacks such proof. Its oddities intrigue, but peculiarity alone doesn't imply purpose. Nature abounds with bizarre, yet organic occurrences. Then why delve into this topic? Because bold assertions spark rigorous investigations. When folks suggest that Atlas could harbor encoded data, sparking fresh polar expeditions or radio surveillance efforts, and the results turn up empty, yet uncover novel insights into dust behavior or coma mechanics along the way, the assertion proves valuable despite its inaccuracy. Scientific advancement doesn't solely come from validating ideas, it also thrives on disproving them. And to conclusively dismiss the notion of encoding, we must treat it with enough gravity to examine it properly. A note on media handling. We'll avoid blending casual blog musings with vetted research. Visual references will clearly separate scholarly articles from personal views. If we mention a claim about encoding, we'll specify the originator and clarify if it's a formal publication or just an online entry. Openness builds credibility. The concept of concealed signals is an engaging mental exercise, one that honors physical laws while exploring the edges of possibility. Yet ultimately, the observations don't support it. Atlas appears as a commonplace, celestial body with distinctive traits. And those quirks, frustrating though they may be to embrace, align with what you'd anticipate from surveying the vast array of solar setups scattered across the cosmos. No two systems match. Each cosmic wanderer will catch us off guard. That's not evidence of design. It's a reminder of our vast ignorance. Regardless of whether Atlas is organic or engineered, timeless or simply aged, a comet or fragment or artifact, It warps our perspectives on beginnings and sources. It compels us to face the boundaries of knowledge and the gap between an object's presence and our capacity to follow its roots. Therein lies the deeper inquiry. Section 14. The existential crux. Allow me to restate the core puzzle as straightforwardly as possible. Oumuamua, Atlas, is a tangible entity. It possesses weight. It follows a path. It bears composition. It is here. Yet from our present observational reach, its backstory remains irretrievable. We can't connect it to a birth star. We can't tie it to a stellar brush. We can't rebuild the sequence of pulls that guided it our way. The entity endures. Its chronicle has vanished, not for lack of occurrence, but because cosmic record-keeping has jumbled the accounts past salvage. This isn't a true contradiction. The laws of nature allow origins. Atlas got hurled from some solar realm. That hurling stemmed from events. The star behind the hurl lingers, or once did amid the stars. The route that drew Atlas near us formed through countless tugs spanning eons. All that transpired. Cause and effect hold firm. But traceability of causes, the knack for piecing together the sequence from what's visible now, that can crumble. Not from any deliberate concealment by reality, but from the fade of details. Disorder prevails. Turmoil prevails. Existence doesn't guarantee us a backstory. Consider this parallel. Picture stumbling upon a flask washed ashore. The flask exists. It's made of glass. It clings to shellfish. It sloshes with liquid. Yet no note, no tag, no etchings. You're driven to pinpoint its source. So you study sea flows. You simulate the float. You trace paths in reverse. But the waters have churned for years. Tides alter. Tempests rage. Swirls emerge and fade. When you attempt to backtrack the course, the array of potential launches has ballooned. The flask hailed from some spot, but now that spot stretches across endless shores for miles. The flask persists. Its birthplace eludes grasp. Atlas mirrors the flask. Our galaxy serves as the sea. 10 million years marks an immense voyage. I'll touch briefly on a few physical ideas as poetic stand-ins, not direct assertions about Oumuamua. Retrocausality, the concept where outcomes might outpace triggers in select quantum or relativity scenarios. Loop timelines, relativity solutions permitting, theoretically, a return to the past. Time arising from disorder. The view that duration emerges from increasing mess rather than standing alone. These don't pertain to Oumuamua. Atlas travels as a straightforward body in everyday space-time, yet they serve as apt images for how origins can persist even as their threads slip from view. The framework permits it, the records do not. From a folklore perspective, the motif of the errant rock. Tales across countless traditions speak of rocks plummeting from above, rocks emerging from nothingness, rocks bearing no lineage. Certain legends deem them divine dispatches. Others view them as portents. Contemporary inquiry sees them as falls from space or icy bodies, with traceable roots in nature. But Atlas shatters that mold. It's an errant rock beyond tracing, and that revives the ancient motif, not by forsaking reason, but by meeting a barrier that lore has long acknowledged. Certain journeys lack guides. Scientific philosophy offers a key insight on this point. The lack of evidence doesn't prove something's missing. We haven't located the star that birthed Atlas yet. That's just a gap in our data. It doesn't rule out its existence. But consider the other angle. With incomplete catalogs, restricted search ranges, and traceback techniques capped at a 10 million year limit, that missing evidence begins to feel like a solid barrier to knowledge. It's not mere unknowing, it's a constraint. The difference is crucial. Ignorance can be overcome through extra work, but constraints demand fresh approaches and instruments. What shortcomings in our current setup does Atlas reveal? Gaia stands out as remarkable, charting more than 1 billion stars with remarkable accuracy. Yet it falls short in places. Radial velocities are available only for the brighter objects. Parallaxes work mainly for those nearby. Faint stars past a few hundred parsecs go uncovered. If Atlas's origin star is a red dwarf 500 parsecs distant without a known radial velocity, we'd miss it no matter how long we search. Mapping the interstellar medium is even patchier. Detailed profiles of gas and dust densities and speeds along random lines of sight simply don't exist, so predicting drag or disruptions from those interactions remains out of reach. These issues are addressable, though they call for advanced surveys and spacecraft that aren't available now. So here's a call to action. Propose specific improvements to narrow the uncertainty for future interstellar visitors. Follow-on missions to Gaia with fainter magnitude thresholds and expanded radial velocity data. Full-sky observations monitoring proper motions for stars down to 15th magnitude or dimmer. Three-dimensional mapping of the interstellar medium via distant quasars and pulsar signals to chart gas distributions. Refined models of the galaxy's gravitational field, incorporating dark matter clumps and evolving structures like spiral arms. Additional ESO observations to compile stats on populations, helping distinguish the typical from the unusual. All these steps are within technical reach. They just need investment and patience. Let me revisit an earlier motif. Chemistry combined with polarization and motion provides three essential clues. Any pair falls short of unlocking the full tale. Chemistry reveals composition and suggests origins. Polarization sheds light on dust properties and alterations. Dynamics reveal the path traveled. In the best case, all three align into a unified narrative. For Atlas, the chemistry stands out as odd yet promising. Polarization is unusual but can be rationalized. Dynamics evade tracing. We've got two of the three clues, but the last one is jammed tight. Thus, we end up with an incomplete view, more outline than full image. Now, the heartfelt part. I won't dodge feelings here, since science springs from people with emotions. Atlas serves as an envoy from 3 to 11 billion years back. It has journeyed greater distances and durations than any creation of ours. It has witnessed countless stars, nebulae, and supernovae. It bears the chemical signature of a planet we'll never reach, a solar system beyond our charts, a past forever lost to us. And that's profoundly humbling, not discouraging or empty, just humbling. It underscores how vast, ancient, and intricate the cosmos is, beyond what our observations can grasp. And that's fine. Boundaries aren't defeats, they're guides. They point to the next frontiers. So, we've followed Atlas's trail as far as possible. We've examined its coma, dust, and trajectory. We've explored bold hypotheses, rejected a few, and held on to others. Yet the narrative doesn't close with dissection. It concludes as the object itself departs. For Atlas arrived not to linger, but to transit, and now it's receding into the void. What remains isn't resolution, but sharper inquiries. Part 15, The Endless Voyage. Allow me to sketch the scene. From September 29th to 30th, 2025, 3I Atlas sweeps by Mars at roughly 29 to 30 million kilometers. Swarms of probes observe. Mars Express angles its instruments. Maven captures plasma effects. Surface rovers attempt sightings, even if it's too dim for naked eye views. Then, on October 29th to 30th, perihelion arrives. Nearest pass to the Sun at about 1.36 to 1.4 astronomical units. Solar warmth intensifies. Any hidden water ice ought to begin vaporizing. The CO2 to water balance could change. Non-gravitational forces might emerge. Ground and space-based telescopes monitor closely. Afterward, Atlas arcs away, beyond Earth, beyond Mars once more, toward the asteroid belt, toward Jupiter's path, and ultimately returning to interstellar realms. Let me summarize the solid facts again, the bedrock we rely on. No origin star identified. Periscuto simulations ran 10 million years of orbits against millions of Gaia catalog entries. 93 close approaches noted. None dynamically significant. The nearest imparted just a velocity change of 0.5 mm per second. Too slight, too distant. Coma rich in carbon dioxide. JWST detected a CO2 to water ratio of 7.6 plus or minus 0.3. One of the richest ratios recorded in any comet. Prominent at 3 Australian dollars, where water typically leads, but not so overwhelmingly here. Profoundly negative polarization low point arrow. The comet experienced a -2.7% shift at a 7 degrees phase angle. An inversion occurred at 17 degrees, featuring an unusually profound and confined profile. Nothing comparable exists among solar system bodies. No signs of non-gravitational forces have appeared so far. The active coma shows asymmetry toward the Sun, Yet no clear rocket-like influence on the trajectory has emerged to date. This situation might evolve near perihelion. The nucleus's dimensions remain unclear. Hubble's observations set an upper bound around 5-6 kilometers, though it could measure just a few hundred meters. We can't confirm, yet since the coma obscures it, what additional insights might emerge post-perihelion as water production intensifies? Should the CO2-to-water ratio decline with nucleus warming, it would support models involving thermal lags. If the ratio holds steady, it would back theories of inherent makeup, where non-gravitational effects become evident through parameters like A1 and A2 in orbital calculations. If these parameters manifest and align with water jet patterns, standard comet behavior prevails. But if they fail to appear amid robust water output, we'd face a real enigma. We could also explore shifts in dust traits, polarization across various phase angles after perihelion, grain size via brightness decline, and spectral analysis for minor compounds. With better signal-to-noise ratios, a prime imaging opportunity arises in mid-December 2025. That's the optimal Earth-comet alignment before Atlas dims against the stellar backdrop. Then come the final clear views. High-res images might capture more. Perhaps a single JWST observation if scheduling permits. Radar efforts could try if proximity allows, but that's improbable. After that, quietude. Atlas will grow too dim, too distant, too swift. It will dip beneath observable thresholds, leaving us with collected data and unresolved queries. Step into the timeline for a moment. We're witnessing the detection and study of merely the third verified interstellar visitor. Half a century back, interstellar objects were unknown concepts. 2 decades ago, models suggested possibilities without confirmations. A decade passed. Oumuamua sparked more mysteries than solutions. 5 years on, Borisov hinted that such interlopers might be routine. Today, 3I challenges every norm. History plays out before our eyes. Data releases, AR-14 preprints, media announcements, all in the now, and soon it ends. Atlas departs, and we shift to whatever follows. But consider this perspective to close, the rootless viewpoint. Perhaps origins fade over time in a restless galaxy. By the time wanderers reach us, their histories might blur irretrievably, not from secrecy, but because the galaxy ages tumultuously and knowledge erodes. The cosmos could teem with foundlings, not forsaken, but separated by eons. 10 million years stretches far, records fragment, and disorder triumphs. Allow me one last speculative musing, marked purely as thought, not assertion. What if certain cosmic entities defy tracking and invite tasting instead? What if the key inquiry shifts from whence your origin to what constitutes you? What if these interstellar drifters serve as the galaxy's method for dispersing chemistry over vast distances, blending substances from stars that never cross paths? No signals, no scouts, just raw stuff. Grains, frost, organics, volatiles, tumbling through eons, touching alien suns, fertilizing worlds, or evading notice until snagged by primate-wielded scopes. What if Atlas conceals nothing of its history? What if we've misplaced it? Let this closing narration echo as the image dissolves. Perhaps 3I's Atlas hasn't shed its origins. Perhaps we've misplaced ours. The Milky Way flows like a vast sea, Atlas a vessel adrift, currents surging for 10 million years. The vessel endures. The sea persists. But its starting shore? Erased, eroded, vanished into endless flow.